Good morning. I'm going to start up here. Before I actually get into the presentation, I'm going to direct your attention. We have a couple people handing out tickets. Please pick up a ticket, go by the booth, see our demos, and you can redeem those tickets for a chance at Starbucks gift cards. And, oh, not a chance. Everyone gets a Starbucks gift card and a t-shirt. So grab your tickets, go over to the booth after the presentation, and enjoy. So my name is Rory Bolt. I'm a senior fellow with Kioxia, and I'll be talking about how we can use SSDs to enhance vector data scaling in generative AI systems with an emphasis on retrieval augmented generation. Oh my. And so, wouldn't you know? All right. A little bit of background here. I think it's fair to say that AI has drastically had an impact on storage. SSDs are in fact used in all aspects of the AI workflow and data pipeline, from ingestion to training to inference, and of course, where I'll be focusing in on the grounding of inference using Retrieval Augmented Generation, or RAG. So today's large language models have been created at great expense using tens of thousands of GPUs and taking, in some cases, months of processing time to create. They've been generously donated into the public domain for use by enterprises, but they have some limitations that we'll be talking about. So these large language models represent an opportunity to monetize AI investments by inference and delivering answers to problems. And the issue with the large language models are they're trained on public data sets. And as I said, they can take months to train, and so they can be slightly out of date with the latest information. Retrieval Augmented Generation is a mechanism that allows enterprises to take their private data, create embeddings and vectors that can be fed into a vector database that then in turn can be used as part of the query process to supply context into the large language model and give results that are more timely, more domain-specific, and more accurate than generalized large language models can produce. Today, these vector databases are almost all implemented in DRAM. And because the vectors, the indices, the quantizations are all held in DRAM, it effectively creates a scalability limit or a memory wall. And these databases are scaling at an exponential rate at this point. So Microsoft did some foundational work in this area because they saw the trend of scaling vector databases and realized that they were going to reach a point where, as the number of vectors in these databases grew, you're consuming more and more memory. And you can either reach a physical limit to how much memory you can install into the systems, or in fact, you can reach a point where it's not economically feasible for you to scale your vector databases. And again, scaling the vector database can improve the accuracy and the quality of the results. So Microsoft did some foundational work in a technology that's called disk-ANN, which allowed them to move the vector database out of memory to SSDs. It allows the vector databases to scale to even larger numbers of vectors that they can handle, while reducing the amount of memory that was required to do this. And so this was a transformational advancement in the algorithms used for approximate nearest neighbor searches that are employed by the vector databases to use the private embeddings that were created by the enterprises to improve the quality of the results. So a typical question that comes out is, okay, if you're moving these vector databases from DRAM to SSDs, what's the impact, right? So on the left-hand side, we're showing the DRAM footprint necessary as you scale the amount of vectors in these RAG databases from 1 billion vectors to 10 billion vectors to 100 billion vectors, and the trend is going towards 1 trillion vectors in these large vector databases. And you can see that as these vector databases scale, the requirements on DRAM go into the tens and even hundreds of terabytes of DRAM necessary for the large vector databases. On the right-hand side is a graph of query accuracy as opposed to the number of queries per second. And as you move to the right on that graph, you're increasing the accuracy, but that's at a computational cost that reduces the number of queries that you can perform per second. Okay? Once again, this is the baseline of HNSW all-in RAM vector database solutions for retrieval augmented generation. So this is the work that Microsoft did by creating DiskANN. And you can see that they're keeping the size of the DRAM footprint required for the vector database down in the low terabytes, but for a vector database of 1 billion to 10 billion vectors. But as you scale out to 100 billion, you're crossing over 10 terabytes again. And once again, if you go out to 1 trillion, which is where we're all headed, it gets even larger. But a huge advancement here. The interesting thing about this is that by changing the algorithms, and this is a combination of quantizing the vector data themselves, as well as separating the full vectors from the quantized data and the indices, they were able to both reduce the footprint, but as you went to higher query accuracies, they reached a crossover point where they could make an SSD-based solution outperform a DRAM solution. And that's sort of a fascinating result, but once again, that's an algorithmic change. They're not exactly an apples-to-apples comparison because they're different algorithms, but very, very promising results. These are actually in production now in some of the Azure cloud offerings, where their Cosmos DB is using this technology under the hoods. So this is a really great improvement in scalability, but at Kioxia, we actually wanted to see if we could improve this further. And so we introduced a technology, a research project that's going to be contributed to the open source called ISAC, or All-in-Storage ANS, with product quantization of the vectors themselves. Okay? And so the idea here is to transfer or transition from mostly in storage to all in storage on the vector database indices themselves. And as we point out on the left-hand side, it's not that we eliminate the DRAM footprint. It's just too small to show up on this chart relative to the other solutions. It's about 100 gigs constant, regardless of the size of the vector database that's required. And so we view this as essentially removing the limitations of scalability of vector databases for retrieval augmented generation systems at scale. As part of this, there's a trade-off. I mean, there's almost always a trade-off. And the trade-off that we made was we consume a little bit more on the SSD side. We fundamentally didn't change the Microsoft algorithms, and the first-order determinant of performance with the Microsoft DiskANN is the number of SSD accesses that are required to perform the query. And with the Isaac enhancements to disk ANN, we've kept that constant. So we're not performing any more accesses than disk ANN did with its algorithms. However, the accesses that we are performing are slightly larger accesses. So the average access size went from a 4 kilobyte read to an 8 kilobyte read. This slightly decreases the performance, but once again, we can still reach that crossover point where a SSD-based approximate nearest neighbor search can outperform HNSW, an all-in-DRAM solution. So we think that this is very, very promising and a great advancement in the accuracy and scalability of retrieval augmented generation systems, or RAG systems. And so with that, I'm going to call out that we are demonstrating this live in our booth. So we have both an HNSW solution as well as a Isaac disk ANN-based vector database solution running side-by-side direct comparison on the same data sets. You can see the performance. You can also take a look at our latest SSDs that we offer for both the data center scale-out storage solutions, as well as SSDs that are optimized for the NVIDIA reference designs. And again, if you take those raffle tickets that have been handed out, go over to our booth, see the demo. You can redeem them for both Starbucks gift cards and a free Kioxia t-shirt. All right? So, thank you very much, and please visit our booth.